Today, we're going to unpack an absolutely incredible 25-year journey, the story of how we taught machines to see. We're going to look at how we went from these clunky, simple rules that could barely find a face to mind-blowing AI that actually understands our world through language. Okay, so let's just dive right in. This one question, right here, what is where? This is the heart of it all. This is the entire field of object detection. You see, it's not just about figuring out if something is in an image. It's about knowing exactly where it is and telling it apart from everything else.
And you can see the jump in complexity right here. I mean, classification is just a simple yes or no question. But detection? Whoa, that needs a whole different level of spatial understanding. Answering what is where is a fundamentally harder problem, and for like 2 decades, the smartest people in AI have been chasing after the answer.
So our story kicks off back in 2001. This was an era that was really defined by one simple rule. If you can't be powerful, you gotta be clever. You know, computers were slow, processing power was super precious, and the big challenge of the day was finding a human face in a photo. Not in a few minutes, but in real time. The solution wasn't more horsepower, it was just more cleverness. I mean, just think about it for a second. Every single picture has millions of pixels. Trying to scan all of them for a face on the hardware they had back then, it was a total non-starter. So the first huge breakthrough, the famous Viola-Jones detector, it didn't even try to solve this with raw power. It solved it with a bunch of incredibly clever shortcuts. So here's the first trick. Instead of crunching the numbers on pixel values over and over again, the algorithm created this pre-computed map of all the pixel sums, called an integral image. What that meant was it could calculate features almost instantly, no matter how big of an area was checking. It was a massive, massive speed-up.
And the second trick was something called an attentional cascade. The best way to think about it is like a series of security checkpoints. The first check is super simple, super fast, and its only job is to throw out the obvious stuff that isn't a face. The next checkpoint gets a little tougher. This whole cascade structure meant the computer could instantly toss out like 99.9% of the image and focus all its expensive processing power only on the little bits that actually looked like a face. So clever.
Okay, let's fast forward to 2014. The game completely changes. The big shift was away from human cleverness and towards machine learning. For more than a decade, humans had been sitting there, carefully handcrafting all those clever rules. But now, with deep learning exploding onto the scene, we could build networks that learn the best features all by themselves.
So the first really successful deep learning detector was called RCNN, and it used this 2-stage approach. First, it would generate about 2,000 regions of interest, basically little patches where an object might be. Then, it would feed every single one of those patches into a powerful neural network, a CNN, to see what was there.
And the accuracy, it was incredible, a huge leap forward. But there was a massive problem. Running that powerful network 2,000 times for every single image was, well, it was disastrously slow. 47 seconds per image might be fine for a research paper, but in the real world, it's completely useless.
The breakthrough came with its successor, Fast RCNN, and the idea was so simple but so profound. Instead of processing 2,000 overlapping little pictures separately, they thought, why don't we just run the big network once on the whole image to create this high-level feature map, and then apply the regions to that map? This idea of shared computation was a total game changer.
And the final piece of this puzzle was faster RCNN. It basically got rid of that slow external algorithm for proposing regions entirely. Instead, it built a tiny little neural network, the RPN, that learned how to propose the regions itself. This turned the whole thing into one single unified network. And that became the first truly viable, almost real-time deep learning detector.
Now, this breakthrough was so big that it kicked off this fascinating rivalry that would really define the next 5 years of research, a frantic race to find the absolute perfect balance between speed and accuracy. So, on one side, you had these precise, methodical, 2-stage models, like faster RCNN. Think of them as the careful surgeons. And on the other side, this new breed of 1-stage models comes bursting onto the scene. You've probably heard of them, YOLO and SSD. These guys threw out the proposal step entirely. They just looked at the image once and predicted everything in a single shot. They were all about raw speed. And for years, these two approaches just evolved in parallel. It was like a technological arms race.
One team would release a model that was a tiny bit more accurate, and then another team would fire back with one that was a little bit faster. Everybody was hunting for that perfect trade-off.
Now, for a long time, the super-fast one-stage models just couldn't quite catch up to the accuracy of their two-stage rivals. The big problem was that most of an image is just easy background. But then, a huge breakthrough came with RetinaNet's focal loss. It was this clever tweak to the math that basically told the model, hey, stop wasting your time on the easy background stuff. Focus all of your learning power on the rare, hard-to-find objects. And with that, the accuracy gap finally closed.
Okay, so by 2020, progress was starting to slow down a little bit. The next giant leap forward would actually come from making things simpler. You see, whether they were one-stage or two-stage, all detectors relied on this really complex pipeline of hand-tuned parts, like these predefined anchor boxes to guess object sizes and extra cleanup steps. The whole field was just ripe for a totally new idea.
And that new idea? It came from a completely different field, natural language processing. The transformer architecture, which had already turned the world of text upside down, was about to do the same thing for how machines see images.
The DETR model introduced this idea called object queries. So instead of plastering an image with thousands of guesses, DETR used a small, fixed set, say 100, of these learned queries. The best way to think of it is like having 100 detectives. Each detective is independently assigned to go out and find one and only one object in the scene.
And because each of those little queries was responsible for its own object, the model just automatically learned not to produce a bunch of duplicate detections. This one change radically simplified the entire pipeline. It just threw out years of complex hand-engineered stuff that everyone thought was necessary.
And that brings us right up to today, to the modern era. And it's all about breaking free from predefined labels and just embracing the incredible power of language. The very definition of what an object detector even is changing all over again, and it's all thanks to large language models.
You got to remember, for their entire history, detectors were closed set. If you trained a model to find cats and dogs, that's all it could ever do. You couldn't ask it to find a screwdriver. It just didn't know what a screwdriver was. But now we've got these new models like YOLO-World, and they can do open vocabulary detection. You can just give them a text description of anything you want to find, and they'll find it, even if they've never seen that exact object before.
And it gets even crazier. State-of-the-art systems like Grounding Dino don't just find objects based on text. They actually comprehend the language to understand relationships and context. They can tell the difference between two really similar things based entirely on what you ask them in plain English.
When you look back, this whole 25-year journey has really been a story of climbing a ladder of abstraction. We went from handcrafting features from raw pixels to learning representations from those features, to replacing all the complicated heuristics with direct prediction, and now, finally, to abstracting away fixed classes altogether and just using universal language. And this kind of leaves us with a final, mind-bending thought. We started this journey with a really simple goal: just find a face in a picture. And now we're building systems that can find an object based on the phrase, "the cat that just knocked over the vase." It really makes you wonder, right? At what point does this stop being simple pattern matching and start becoming something that's actually beginning to reason about the world?